Hi, everyone. Today, I'm very excited to be presenting our work called PageFlex, which is a step towards improving memory efficiency in today's data centers. OK, so why do we need to improve memory efficiency? I don't think this is a surprising question to anyone here. DRAM cost scaling has nearly flattened in the recent years, and more than half of the server's expense today is coming from, or is going to very soon come from, spending the cost on DRAM. So given that, there's been many efforts to improve memory efficiency in data centers and alleviate some of these costs. And the most prominent of which is to find any idle data that is sitting in memory and then offload it to other cheaper substrates like compressed DRAM, tier, or SSD. But these substrates are generally much slower, so you have to find very infrequently accessed, or what we call cold data, and then offload that to avoid any impact to application performance. Fortunately, well, there's a lot of it. Many studies from hyperscaler data centers show that even by a conservative definition of cold memory, of data not being accessed in minutes at a time, there is ample amount of data that you can offload without any significant performance impact. So naturally, there has been production deployments at hyperscalers like Google and Meta, where they do have systems doing this at large scale. To offload cold data, these systems employ OS paging mechanisms that already exist, that are designed to transparently offload pages to swap. And to find cold data, they reuse these LRU approximations that are available in the Linux kernel. Well, LRU is generally good when you are trying to be workload agnostic, but we can definitely do better if you know something a little bit more about the workload. In fact, there are a ton of examples in literature in various caching contexts where folks have designed different policies that beat LRU for like specific workloads. In fact, we've seen that in our simulations as well, where one of the things that we try to find out is like, what's the difference between, well, what is the difference between the memory that you can offload by using the LRU policy compared to what the optimal policy can give you. We did this on a set of page traces from real-world applications, and of course, what we find is that there's a significant room for policy improvement here. So given that, we want to be able to change the policy and experiment with like different policies. But the challenge is current deployments are OS paging based, and while that is good for a number of reasons, right? You get transparency for the applications, and you get to reuse these swapping mechanisms that are designed to support a variety of backends and well integrated with like mechanisms like C groups, et cetera. But that does mean that your policy code is limited to the OS, and that affects what we call policy fungibility, the ability to easily experiment with policies and roll out these policies in a fast fashion. Because OS code, this is, I'm sure folks know this, like OS code, debugging in OS code is generally challenging, and there are upstreaming concerns when you're trying to write specialized policies, and bugs in the OS code are high risk and have like a large impact. So that tends to that tends to sort of affect policy fungibility. So we want to take this policy out of the OS code, and there are like existing alternatives. The most prominent one being just discard the OS mechanisms and then provide the memory through an application library. But what this does is introduce a custom memory interface that is going to invite application changes. So this is really not going to be practical for hyperscalers, at least like at the current state of things, where you do have some automation of this porting effort with compilers, but I don't think we are quite there yet. The other option, if you still want to keep the application transparency, is to use a mechanism called userfaultfd, which breaks the mechanism and keeps the page tables intact in the OS while moving the swap stack into the user space. While this can provide better flexibility policy-wise, it still does bring that entire swap stack into the user space and hurts compatibility with existing deployments. More importantly, though, because again, it brings back that path back into user space, so it adds more user kernel transitions, and it adds more overhead to the paging paths and slow down the application. So even exporting the part of the mechanism seems to bring out these compatibility and performance overhead issues. So the question that we're really asking is, really, so can we externalize policy while still keeping the mechanisms intact? So our answer is PageFlex, and I'm going to show that PageFlex provides policy fungibility, but keep most of the rest of the, but still checks like the rest of the constraints. So let's try and understand like a couple of key observations for PageFlex. The first thing is that we want to keep the mechanism intact in the OS, which means all the access signals that your policy gonna need and the enforcement mechanisms for paging are gonna be in the OS. So any chance, we cannot really put anything that policy that runs in sync with these paging paths out without adding overhead. So what PageFlex does is focus on the policy that you can run asynchronously and then put that, try and externalize that. Fortunately, the use cases that we care about, like proactive offloading and prefetching, are something that we can do asynchronously. The other question is, okay, now that we have the policy out, what kind of information do you want to gather and then export to user space to provide enough flexibility to be able to implement all these policies? So to sort of answer that question, maybe let's look at what current policies do. So for offloading, for example, there is you periodically scan the page tables, looking at these access bits, and then you try and implement some policy like LRU, where you maintain an age per page, which gives you an ordering on the pages, and then you decide like at a certain point you're gonna take the pages out of the memory and put it into disk. So that's how the current existing LRU works, right? And similarly for prefetching, you look at the stream of page faults, detect a sequential trend, and try and like prefetch the pages that come later in that trend. What we sort of observe is that even for most policies, like all you need to, the signals will remain the same, and you can try and you can implement like a lot of these policies by just generalizing some aspects of this. For example, with the offload, going from LRU to other policies, all you need to do is generalize the weight, maintain a generalized page ordering, and then you can define this weight in a custom way so as to be able to implement different policies. The same thing applies for prefetching, where all you need to do is look for a different trend, and you can again similarly implement other existing policies. So really the second observation is that by having customization at these few well-defined events, maybe throw in some per page state, you can implement most of these policies. And that's good news because we can do this with eBPF in the kernel without having to export all this data to user space. So a really, really quick overview of the entire system. PageFlex provides the ability to add, subscribe to any of these events that we track for each page, and policies get to provide the handler functions, customizable, where they can customize the policy at each of these handlers and make policy decisions as well. And we also reserve some space in the page struct and provide safe access to the policies so they can maintain this per page state. Once the policies make decisions, or maybe they want to digest the data, they can send that to user space for a more complicated policy execution. And once you have the decisions, we use the madvise interface to implement the page in and page out. So we show that this particular model is enough to implement many policies. Without going into the details, we were able to implement many offload policies, existing offload policies in a few lines of code. The same goes for prefetching as well. All we had to do was map those models that I previously mentioned to the design here. So PageFlex is able to implement existing policies with all these lines, again, written outside of the kernel, whereas previously they were written inside the OS code. So PageFlex does with very little overhead. I'm going to show that with like the set of charts in the next couple of slides, where I compare different implementations of the same policy, which is LRU in this case, that are implemented in the kernel. And I'm going to show you the Redis performance on the left as I increase the amount of data that I put into into the swap. And on the right, what you see is the policy functionality. So that should stay the same as I go through various implementations of the same policy. With userfaultfd emulation, we noticed that there's a significant drop in performance, up to 15% at the right. And PageFlex is able to recoup all that performance and basically perform the same as OS implementation. So it's not just the simple policies. PageFlex can provide further policy specialization. So for example, you can implement multiple policies within the same application because access patterns may vary across space and time, and you may want to try and implement multiple policies for different, either different regions, or like if you have different access patterns across time, you may want to try different policies across time as well. So region aware and phase aware. Without going into the implementation, we were able to show that these sort of policy specialization modalities, we were able to improve performance of like a key value store, not performance, but yeah, we were able to offload more memory for a key value store at the same performance by using these specialized policy variants for different client workload patterns. So, that's really the highlight. This sort of shows how PageFlex can unlock benefits of policy specialization. By again, like all these policies are written entirely in the user space and eBPF code. So to summarize, paging policies dictate how much memory you can offload to these cheaper tiers, and current systems use OS-based policies which are harder to evolve. PageFlex provides a clean separation of policy and mechanism, and it can enable you to write policies outside of VS Code, but while still being fully compatible with existing deployments and at a low overhead. Thank you, and I'll take any questions now.